Hola, amigos. Soy el profesor de momentum, por supuesto. And today we will discuss solving problems that involve the conservation of momentum and then also some impulse stuff as well. Please read this problem and pause it and see if you can solve this conservation of momentum problem. Now, hopefully you have seen that it is a conservation momentum problem because there are no external forces that are going to be acting on it, and all conservation momentum problems can be started by saying that initial momentum equals the final. And then you should say, for your initial, you've got the total mass of the 1300 times the initial velocity, and then splits in two, and you've got the mass of the nose cone times the velocity of the nose cone, and you add that to the mass of the ship and the velocity of the ship. If you didn't set it up like that, pause it, do that, and then you should be able to solve it. Now, let me help you out a little bit. We're going to plug in our 1300 kilograms for there, the 250 meters per second there. Mass of our nose cone, 3,500. Velocity of the nose cone, we added 90 meters per second to the already 250 that we had already. That's going to be our 340 meters per second. And then the mass of the ship, what's remaining on it, is going to be the 1,300 kgs minus that 3,500. So that's going to give us, I believe, 9,500 kgs times the velocity of the ship. Now it's just a matter of algebra. And here I have filled in some algebra for you, so pause it, check, and see that your algebra works out the same as this stuff does, and the units should work out as well. Caramba! Ahora es muy loco! Because we are getting into 2 dimensions of momentum loco-ness. However, the means of solving is still the same. You're just going to have to deal with an x direction and a y direction. So pause it, see what you can do with this one. When you're dealing with 2 dimensions, you want to break things into components and deal with one direction at a time. Maybe the x, and then maybe the y. We will start with the x direction. And just as we did in the last problem, we're going to say that momentum initial equals momentum final, but we're going to do it in the x component only. Initially, we only have momentum from this guy. This guy has 0 x momentum, person B. So we say that the mass of A times the velocity of A. After the collision, they then stick together. So we've got mass of A plus mass of B times the velocity of that thing in the x direction only. And then we can start filling in a few things. That A is going to be the 1,200 times the velocity of A. That's what we're looking for, isn't it? Yeah, we don't know that. Once they're stuck together, they're going to be 2,500. Now this velocity is going to be the x component. So that's going to be 5 meters per second times the cosine of 45 degrees. Now it just becomes algebra. Do it. So here you have it. Here's the answer for the x direction, the speed of this car on the A. Now if you want to find the speed of the car in the b direction, or the vertical, you do the same thing, except you consider only vertical stuff. Pause it, see if you can finish that if you haven't already. Now to help you out, say that initial in the y equals the final in the y, and we have, as before, only the mass of the b object, so velocity of the b object. The mass of both of them stuck together, which I'm just going to go ahead and put in as 2,500, times the velocity in the y component, which is going to be 5 times the sine of 45 degrees. Now the 45 degrees makes it easy because that's the same as we had before. So to just fill in a few things, I'm going to end up with 1,300 times VB. This comes out to be the same, 8839, and then we end up with a velocity of B. I believe that was about 6.8 meters per second. Here's an impulse problem, and there's even a force versus time graph. So pause this one, see if you can solve it. Now, if you know that impulse is equal to force times delta t, hopefully you also know that impulse is going to equal the area underneath this time graph. And we probably want to break it into a triangle, a square, and maybe another triangle. So this area, which is the impulse, is going to be, for the first triangle, 1/2 base times height, plus just the base times height here, plus, again, the 1/2 base times height. So we will have 1/2 of 5 seconds times the 8 newtons, plus the 7 seconds times 8 newtons, plus the 1/2 again, 5 times 8. And we are going to end up with 20 newton seconds, which, remember, is also a unit for impulse or momentum. Plus 56 newton seconds plus another 20 newton seconds, and that's going to give us a grand total of, I believe, 96 newton seconds. Woo! Lo siento, arriba y buenas noches.